Hello everyone. Today's topic is industrial sensing and actuation. The Industrial Internet of Things is the application of IoT technologies in industrial settings such as manufacturing, engineering and automation. And industrial IoT, it connects machines, sensors and software to optimize operations, improve the efficiency and enable real-time decision making. The core elements of IoT, that is the industrial IoT, includes sensors, actuators, data analytics and the connectivity. Industrial IoT, it is a widely deployed in industries such as manufacturing, healthcare, logistics and smart infrastructure, and it also helps industries to achieve predictive maintenance, process automation, remote monitoring and real-time analytics. Industrial IoT, it integrates smart sensors, cloud computing, artificial intelligence and machine learning in order to enhance the operational efficiency and reduce the downtime. Sensors, these are the primary source of industrial IoT data and these are the foundations of industrial IoT as they collect real world data from the machines, equipments and the environment. And these sensors measures various parameters such as temperature, pressure, humidity, vibration and motion. And the collected data, it can be analog or digital and it is transmitted for further processing. The analog sources will provide continuous signals, for example, temperature sensors and pressure sensors. And digital sensors provide the discrete signals, for example, RFID and digital temperature sensors. The intelligence of IoT systems, it is derived from the sensor data through the data processing and the analytics, and advanced artificial intelligence and machine learning algorithms analyze the sensor data to detect the patterns, predict the failures and optimize the performance. And the real-time insights which are generated from sensor data enables the industries to make data-driven decisions, enhance the automation and improve the safety. And actuators are the output devices that execute control decisions based on sensor data analysis, and they convert electrical signals into physical actions and enable the automation process. Examples of actuators are electric motors, which are used in conveyor belts, robotic arms, and hydraulic and pneumatic actuators, which are used in industrial automations, and the smart valves and the relays used in the process control system. Now, what is the need for sensing in the industry? In industrial environments, the sensing technology, it plays a very important role in improving the efficiency, automation and decision making. The sensors enable real-time monitoring of the machines, processes and environmental conditions, ensuring optimal performance and reducing operational risk. The sensors, these will allow the industries to automate processes by collecting the real-time data and feeding it into control systems. Therefore, these provide a high degree of automation, and the automation will reduce human intervention, leading to faster and more precise operations. Examples are proximity sensors in robotic arms, temperature sensors in manufacturing lines, and pressure sensors in hydraulic systems. And these can raise the productivity of the industries by continuously monitoring the equipment and production lines, and also help to identify inefficiencies and the bottlenecks. And the industries can optimize workflow and resource utilization, leading to higher output with minimal waste. Example are vibration sensors in predictive maintenance, which will prevent the machine failures and ensure uninterrupted production. And the sensing, it will also improve the quality, and these will help to maintain the consistent quality standards by monitoring the parameters like temperatures, pressure, humidity, and vibration, and automated quality checks using vision sensors and laser measurement tools will ensure defective products are detected early. Example are optical sensors in assembly lines will detect the misalignments and reduce the defective units. Then these sensors will also help to detect the hazardous conditions, ensuring the workplace safety for employees. So it can provide better safety. Gas sensors, smoke sensors, uh, and you have smoke detectors and thermal cameras. These will alert the workers about the potential risk before accident occurs. And examples for these are the infrared sensors in hazardous environments, which will detect the gas leaks and prevent the explosions. And also it reduces the downtime, where the sensors will enable the predictive maintenance, identify early signs of wear and tear in the machinery, and also it will minimize unexpected breakdowns and reduces the repair cost. For example, IoT enabled sensors in smart factories will track the machine health and schedule maintenance before failures happen. Now we will see what are the requirements for industrial standards in sensing and actuation. In order to ensure the efficiency and reliability in industrial environments, sensing and actuation systems must meet certain industrial standards. These standards focus on accuracy, cost effectiveness, and seamless connectivity in order to maintain the optimal operations. The first point is reliable sensing, where the industrial sensors must provide accurate and consistent data for precise decision making, and they should function under harsh conditions such as high temperatures, vibrations, and exposure to chemicals. Example is temperature sensors in steel plants must withstand extreme heat while maintaining the accuracy. Then you have low cost sensing and actuation, where the cost effective sensors and the actuators are very important for scalability and widespread adoption, and the industry requires energy efficient, durable, and affordable components in order to reduce the operational expenses. Example here is micro electromechanical system, that is MEMS sensors, which offer low cost high precision solutions for industrial applications. Then you have continuous connectivity, where a continuous and uninterrupted communication network, it is necessary for real time monitoring and control, and the wireless technologies like Wi-Fi, Bluetooth, 5G, and wired protocols like Ethernet, then you have Modbus, CAN bus. These ensure seamless connectivity. Example is industrial IoT enabled factories are like they will use the cloud connected sensors for real time predictive maintenance. Then you have industrial sensing. Here we'll see the conventional sensing versus the contemporary sensing. In industrial sensing, it plays a very important role in monitoring and controlling the industrial processes, and it has evolved from conventional sensing, which focuses on local feedback control, to the contemporary sensing, which integrates the Internet of Things for advanced monitoring and decision making. The first type of sensing is the conventional sensing, which which is used in feedback automation within the industrial control systems, and the sensors collect data from the machines or processes, and these will send it to the controllers and the real-time adjustments. And based on the feedback received, since necessary actions are taken as per the system requirements. Example is in a high temperature controlled manufacturing process, a thermocouple sensor, it will detect the temperature changes and adjust the heater accordingly in order to maintain the set point. Second type of sensing is contemporary sensing. where the sensors are connected to the internet, that is the IoT based sensing, enabling the remote monitoring and data driven decision making. These sensors can measure and analyze various aspects of industrial systems such as product lifetime, which predicts wear and tear, ensuring the timely maintenance, and loop efficiency, which monitors the control loops for energy and process optimization. Next point is safety, which detects the hazardous conditions, for example, gas leaks, temperature fluctuations, and these will trigger the preventive actions. Then you have reliability, which enhances the equipment lifespan through predictive analytics and early fault detection. Now we will see what is smart sensor according to IEEE 1451 standard. A smart sensor, it is an advanced sensor equipped with small memory and a standardized physical connection, allowing seamless communication with processors and the data networks. And the key features of the smart sensors are integrated memory, that is it will stores the calibration data, sensor configuration and the processing algorithms, and it will help in self diagnosis and reduces the dependence on external controllers. Then the second key feature is standardized physical connection, where it ensures the interoperability across different systems and allows connection with microcontrollers, IoT devices and industrial networks. And the third key feature is communication with processors and the data networks, which enables the real-time data transfer in order to control the systems and cloud platforms, and supports wired and wireless communication, where the wired communications are Ethernet, Modbus, etc. and wireless communication are Wi-Fi, Bluetooth, Zigbee communications, and many more. Examples are the industrial IoT sensors monitor the machine health and predictive failures, and the smart temperature sensors, these will adjust the HVAC systems based on the real-time data, and the biomedical sensors which track vital signs in wearable devices. Now we will see the components of the smart sensors. The smart sensors, these consist of multiple integrated components that enable accurate sensing, signal processing and communication with external systems. So here the first component is multi-parameter sensing unit, where a single sensor module that can measure multiple physical parameters such as temperature, pressure and humidity, and it will help in reducing the system complexity and improve the efficiency. Example is a smart weather sensor which detects the temperature, humidity and air pressure simultaneously. Then you have analog detection circuit which converts the analog signals like temperature, voltage, pressures into the electrical signals, and this will enhance the signal accuracy and removes the noise before further processing. Example here is a thermocouple sensor outputs an analog voltage proportional to the temperature, which is then processed by the circuit. Then you have digital signal conditioning unit, which converts the analog signals into digital data for further processing, and it performs the amplification, filtering and error correction in order to enhance the signal quality and ensures high precision in measurements before data is transmitted. For example, you have an analog to digital converter in a smart pressure sensor which digitizes the output for microcontroller processing. Then you have interfacing unit to bus, which connects the smart sensor to a communication network or processor via the standardized bus protocols and enables real-time data transmission to cloud servers, industrial controllers or the IoT platforms. And it also supports protocols like I2C, SPI, UART, CAN and Ethernet for seamless integration. Example here is a smart industrial sensor using Modbus to communicate with a PLC, that is the programmable logic controller. Here we'll see a smart sensor node, which is an integrated system which collects, processes and transmits the data for various applications such as IoT, automation and industrial monitoring, and it typically consists of the following components. The first is sensing, where it has sensor and analog detection circuit. So this is the first stage where the sensor detects the physical parameters such as temperature, pressure, humidity and motion and etc. And the analog detection circuit, it processes the weak signals from the sensors and amplifies or filters them as needed. Then you have signal conditioning, where the raw signal from the sensor may need adjustments such as amplification, which is used to increase the signal strength, filtering in order to remove noise, linearization in order to correct the distortions. And this ensures that the signal is in usable format before the conversion. Then you have analog to digital converter, that is ADC. Since most modern processing units, these work with digital data, so the ADC will convert the conditioned analog signal into a digital format. Then you have the processor, where a microprocessor or the digital signal processing processes the digital data, and it can analyze the data, apply decision making algorithms and control connected devices. Then you have actuators. After processor, you have the D to A converter, that is the digital to analog converter. That is, if the system needs to generate an analog output, the DAC converts the digital signal back into the analog form, and this is useful for devices like analog gauges or the audio output systems. And coming to the actuator, if action is required, the actuator responds based on the process data. Example, a motor turning on and off. Then you have a wall opening or closing, a display updating. And here you have communication, memory and user interface. So the processed data, it needs to be transmitted in order to it needs to be transmitted to the other devices or a central server, and the common communication methods includes wired and wireless communications. Then you have memory, which stores the data for processing, logging or later retrieval, and the types of the memory are RAM or flash memory. RAM is for temporary storage and flash or EEPROM is for long-term storage. And then you have user interface, which allows the human interaction with the sensor node, and it includes the LCD or LED display, keypad or buttons, mobile app or the web interface. These are the functions of the smart sensor. So the smart sensors are advanced sensor systems which will integrate multiple functionalities beyond just sensing. And they play a very important or the crucial role in Industry 4.0 and the Industrial Internet of Things by providing enhanced automation, data communication and decision making capabilities. And the key functions of smart sensors are multi-sensing capability, where the smart sensors can detect multiple physical parameters like temperature, pressure, light, humidity, vibration on a single node. And this capability, it is highly beneficial in industrial production units, where monitoring multiple conditions simultaneously ensures the optimal performance and the quality control. Next, you have data communication, where the smart sensor transmits the measured data, calibration values and the compensation data to the central control unit or cloud-based systems. And the communication is done via wired or the wireless protocols. Then you have A to D or D to A convergence, where the sensors, these will often produce analog signals. The smart sensors include the analog to digital and the digital to analog converters in order to ensure the compatibility with digital processing units. And this conversion, it will enable advanced signal processing for improved accuracy and the reliability. Then you have self-decision making, where the smart sensors self-monitor their performance and surrounding environment, and based on the real-time data, they can adjust internal parameters for compensation, trigger alerts for anomalies, and initiate corrective actions automatically or notify the human operators. And the last function is reduced cost, where the integration of the self-diagnosis and the predictive maintenance reduces the equipment failures and minimizes the downtime. And the initial investment in a smart sensor is recovered over the time through optimized efficiency and the reduced maintenance cost. So these are the functions of smart sensor. That is multi-sensing, data communication, A to D and D to A conversion, self-decision making, and reduced cost. Then you have sensing in a milk packaging unit. Now, here it is an illustration of sensing in a milk packaging unit, where smart sensors plays important role in ensuring accurate and efficient filling of milk into the containers. So the mechanism is as follows here. That is, the sensor, first is a sensor installation. A flow sensor is installed in a line with the outlet tap, where milk is dispensed into the bottles or the packets. And this sensor, it is placed to monitor the amount of milk flowing through the system. Okay. Then you have impeller mechanism, that is the working of the sensor. Here the sensor contains impellers, that is, those are nothing but the small rotating blades. These are inside the sensor, and when the milk flows through the sensor, the impeller will spin, that is the blades will spin due to the movement of the liquid. And the speed of the rotation, it is directly proportional to the flow rate of the milk. If the flow is faster, then the blades will move faster. Then you have electrical signal transmission. Here, as the impeller spins, it will generate an electrical signal, and this will be usually in the form of pulses. And this signal, it is sent to the controller unit, that may be a PLC or a microcontroller, for real-time monitoring. Next step is the data processing, that is the data interpretation by the controller, where the controller processes the signal and it will calculate the amount of milk dispensed, and it continuously compares the flow data with the predefined threshold, that is the desired milk quantity per packet or the bottle. Then you have automatic stopping mechanism, where once the set threshold is reached, the controller sends a signal to the sensor that it has to be, the supply of the milk has to be stopped and it has to close the outlet tap. This will ensure that each packet or bottle receives the exact amount of milk, avoiding underfilling or the overfilling. So overall result is, it will ensure the accurate filling, minimal wastage and high efficiency. So this was about sensing in a milk packaging unit. Then you have accessing the sensors and actuators. Now, to interact with the sensors and the actuators, a combination of operating systems and programming languages is used, and the choice depends on the hardware application requirements and the real-time processing needs. So the first is supporting operating systems. Here you have, these are the types of the operating systems which can be used according to the applications. So these operating systems will provide the necessary drivers, libraries and real-time processing capabilities for sensor and actuator control. The first is the Zephyr, where lightweight RTOS for IoT and embedded systems is designed. Then you have Ubuntu, a popular Linux-based OS used for robotics, automation, and industrial applications. Then you have Open SUSE, uh, that is a flexible Linux OS commonly used in industrial automation. Then you have Linux, a Debian based operating system optimized for IoT and embedded applications. Then you have Arch Linux, and it is a lightweight for customizable Linux distribution used in embedded systems. And the last is Android Things. It is a Google based operating system which is designed for IoT devices and smart applications. And the programming languages which are used for sensors and actuator control are C, C++, Java, Python, and Lua. C, it is used for low-level hardware interaction, making it ideal for the microcontrollers. C++, it provides object-oriented features useful for complex embedded applications. Then you have Java, which is preferred for cross-platform applications and IoT frameworks, and Python, which is a high-level language used for rapid development and IoT scripting. And the last is the Lua, which is a lightweight scripting language, which is often used in embedded systems and automations. Then you have the Intel IoT device library for sensors. The first one is MRAA, that is a low-level library, and here it is designed for GNU or the Linux platforms, and it provides a hardware abstraction layer, meaning it is not tied to a specific hardware platform, and it supports I2C, SPI, PWM, UART, making it ideal for interfacing with various sensors and actuators, and it is used for direct hardware communication and the custom implementations. Then you have UPM, that is a high-level sensor API, and here it will provides easy to use APIs for the sensors, and it simplifies the sensor connectivity by hiding the complex low-level details, and it works with industrial grade sensors and ensures integration for real-world IoT applications. And also it allows easier control of sensors without requiring extensive knowledge of underlying hardware protocols. Next is the utility of IoT in industrial subunits. So here the IoT enabled sensors and the smart systems, these will play important role in industrial subunits, enhancing the efficiency, accuracy, and the automation. Now, the first point here is the measurements, where the sensors continuously monitors the patterns like temperature, pressure, humidity, then vibration and the flow rate, and also ensures precision in the industrial processes and compliance with the quality standards, and these will help in predictive maintenance by detecting the anomalies in the early stage. Then coming to the production, here it automates the manufacturing with the real-time monitoring of machinery and the production lines, and it reduces the manual intervention, ensures high productivity and consistency. And the smart sensors, these will optimize the sensor resource utilization, for example, energy, raw materials, etc. And product inspection, here the quality control sensors will detect the defects, then inconsistencies and the deviation in products, and it uses the AI based vision systems for automated inspection and reduces the waste and rework, improving product reliability. Then coming to the packaging and shipping, here automated packaging lines ensures the precise filling, sealing and the labeling, and the RFID and the barcode scanners will track the shipments. These will reduce the errors and the losses, and the real-time logistics tracking, these will optimize the supply chain and the management. Then coming to the industrial sensor calibration, calibration, it is very important to ensure the accuracy, reliability and the consistency in the industrial applications, and also it involves the adjusting the sensor's response to match the actual value, minimizing the measurement errors. Here the purpose, that is a purpose of calibration is to improve the sensor performance by eliminating the deviations from the actual values and ensuring precise measurements for industrial processes, and it corrects the sensor drift and environmental influences over the time. Then you have industrial grade calibration, which uses the advanced signal processing algorithms and onboard circuitry for automatic calibration, and it will reduce the manual adjustments, improving the efficiency and the reliability. Then we have key calibration methods where the calibrate in the actual system is there, where the sensors should be calibrated in the same environment where they will operate to account for real world conditions. Okay, then you have the standard references, that is the use of the standard references, where the calibration is done against known reference standards in order to ensure the accuracy. Then you have proper calibration techniques, where it includes the 0 point calibration, span calibration, and the multi-point calibration for accurate tuning. Then you have regular recalibration, where the sensors require periodic recalibration in order to maintain long-term accuracy, as wear and environmental factors, these can impact the performance over the time. Then these are some of the leading sensor technology manufacturers. The first one is the DTS, that is the Diversified Technical System. Here it specializes in high performance data acquisition sensors for crash testing, biomechanics, and the defense applications. Then you have Bosch, which produces the automotive, industrial, and consumer grade sensors, including MEMS based sensors for IoT and smart devices. Next is Honeywell, which manufactures industrial, aerospace, and healthcare sensors, including the pressure, temperature, and the gas detection sensors. Then you have Masa, that is which is expert in ultrasonic sensor and sonar technology, and it is used in industrial, medical, and the underwater applications. Okay. Next is the Adafruit. So here the Adafruit, here it offers a open source sensor modules and development boards for makers, engineers, and IoT projects. Then you have Omega Engineering, that is which specializes in temperature. Okay, Omega Engineering, pressure and flow sensors for industrial and the laboratory use. And you have Micro Sensor, which produces pressure sensors, level transmitters, and flow meters for industrial automation and the environmental monitoring. Now we have PLC in the industrial applications. So PLC, it is a programmable logic controller. It is a specialized digital computer designed for industrial automation, and it is widely used in manufacturing, process control, and robotics to monitor the inputs, process the logic, and control outputs efficiently. And here the architecture of the PLC, it consists of the CPU model. Okay, and here the CPU model, it has a central processor which executes the logical operations, computations, and the decision making, and memory stores the programs and the real-time data for operations. Then you have power supply module, where it provides regulated power to all the PLC components and ensures the stable operation under industrial conditions. Then you have the input output module, where the inputs connects the sensors, switches, and the user controls to collect the data, and outputs controls the actuators, motors, solenoids, and the alarms based on the logic. Next is you have the industrial applications. The first application is manufacturing automation, which controls the conveyor belts, then robotic arms and the assembly lines, and process control, it regulates the temperature, pressure, and fluid levels. Then you have power plants, which manages the turbines and generators, and last is the building automation, which controls the lighting, HVAC, and the security systems. Now we'll see SCADA. about the industrial applications and the components. SCADA, it is a supervisory control and data acquisition. It is an industrial control system which enables real-time monitoring, process control, and the data analysis across various industries. And it collects the data from the remote sites and it will transmit it to a central system for supervision and control. And the SCADA, it is widely used in the industries like oil and gas, power generation, water and waste management, energy distribution and manufacturing. The key components of SCADA are supervisory system, where the central control system will oversees all operations and processes data and also generates reports and enables the decision making. Then you have remote terminal unit, that is the RTU, where a field device will collect the data from the sensors and transmits it to the supervisory system, and it will act as an interface between the physical equipment and the SCADA network. Then you have SCADA programming, which configures how SCADA systems respond to different situations and involves logic and control sequences for automation. Then you have human machine interface, that is the HMI, where a graphical user interface, that is a GUI, will allow operators to monitor and control the processes, and it will display the real-time data, alarms and the system status. Then you have communication interface. Here it will enable the data transfer between the field devices and the central SCADA systems. And it uses the communication protocols such as Modbus, Ethernet, etc. Then you have PLC, that is the programmable logic controller, which automates the industrial processes with the precise control. Okay, and the applications are, here it is used in oil and gas, then power generation, water management, energy distribution and manufacturing, and also it integrates with Industry 4.0 and Industrial IoT, and it will enable the cloud-based monitoring, predictive maintenance and the enhanced automation. Now you have the industrial control with WSANs, that is the wireless sensor and the actuator networks, where these will enhance the industrial monitoring and control by integrating the sensors, actuators and the wireless communication protocols for real-time automation. And these networks, these are widely used in industrial applications such as HVAC, that is the heating, ventilation and the air conditioning systems, where sensors measure parameters like temperatures and the actuators, for example like wireless air conditioners, which adjust the conditions accordingly. And the key features or the advantages of the WSANs are, it is first is a pre-installed infrastructure, that is it will easily integrate with existing systems. Then you have easy sensor and actuator deployment, where the wireless technology, it will reduce installation complexity. Then you have network self-organization, that is the WSS can dynamically adjust their communication paths and node connections for efficiency. And the last is the low cost, which reduces the installation and the maintenance expenses and eliminates the need for extensive wiring, etc. And the key features of the WSANs are integration of sensors and actuators, where the sensors gather real-time data while the actuators respond based on control algorithms. Then second is the wireless communication protocols, which enables the seamless data transfer without physical writing, making deployment more flexible. And the next key feature is the real-time task scheduling, which ensures timely execution of tasks based on sensor data and the predefined control laws. And you have control law implementation, which defines how actuators should respond based on the sensor inputs, optimizing industrial operations. Okay. Then you have electro-hydrostatic actuation systems, that is the EHA, which is an advanced actuator which combines the benefits of both electric and hydraulic actuators, and it serves as a substitute for traditional hydraulic and the electromechanical actuator, and it offers high force, energy efficiency and the decentralized operation. The key features are hybrid operation. Okay, here hybrid operation, then high force capability, high energy efficiency, decentralized actuation. And the Hybrid operation is it uses an electric motor to drive a hydraulic pump, and it will eliminate the need for centralized hydraulic system, and it provides a precision of the electric actuators and the power of hydraulic actuators. Then you have high force capability, which is ideal for applications requiring heavy loads and the precise control, and it is commonly used in aerospace, automotive, and the industrial automation. Then you have high energy efficiency, like here there is no need for constant fluid circulation, and it leads to low energy waste. Then you have decentralized actuation, which eliminates the complex hydraulic pipelines and the central hydraulic power units. And each actuator is independent, and it improves the reliability and the reducing maintenance. And the key advantages are high force capability. These all are the key features and as well as the key advantages. Okay. Then you have applications where like it is used in aerospace, automotive industry. Then it is used in industrial machinery, etc. Next is electro-pneumatic systems, which combine the advantages of the electric and the pneumatic actuators, and it offers a precise control, efficient communication, and the advanced diagnostics. And these systems use electrical signals to control pneumatic actuators and make them ideal for industrial automation and the high precision applications. Then you have key features or the advantages of electro-pneumatic systems. First is the precise flow control, which will regulate the airflow with high accuracy for smooth and efficient actuator movement, and also it ensures optimal pressure and speed sorry, in industrial applications. And second is advanced communication, which uses a digital interface for seamless integration with the industrial control systems, and it will enable the real-time monitoring and the remote operation. Then you have better diagnostic, which detects the faults earlier, and it improves the maintenance. Then you have ultra high resolution, which enables the fine actuator movement and the positioning. And the applications and the hybrid advantages that here the electric actuator, it will provide precise control and programmability, and pneumatic actuation, it offers fast response time and high force output, and this combination enhances the efficiency, reliability, and adaptability in the automation. Applications are manufacturing automation, medical equipment, and the aerospace and automotive control. These are the manufacturers of the actuator technology. So first is the Moog. Okay, so here it is used like these following companies. These are specialized in actuator technology, and this will offer a wide range of electric, hydraulic, pneumatic, and electromechanical actuators for industrial, aerospace, and the automation applications. And here the first industry is I'll pronounce it as Moog, that is MOOG. Here this will provide electro, hydrostatic, hydraulic, and the electric actuators, and the industries which use such type of actuators are aerospace, defense, industrial automation, and the medical equipment. Key features are key features of such type of actuators are, these are high precision motion control solutions, and these are used in aircraft control systems, space exploration, and industrial robotics. Second is the SKF, that is the Svenska Kullager Fabriken. Okay, and here these will produce electric and electromechanical actuators and used in industrial automation, robotics, and automotive. Then you have KNR systems, which will produce electric linear actuators and motion and control systems used in industrial automation, semiconductor manufacturing, medical devices. Then you have FUYU automation, which will produce electric linear actuators and the robotic automation components, and used in CNC industries like CNC machines, 3D printing, semiconductor equipment. Then you have SPAT, that is a specialized precision actuation technology. Okay, so here these will produce the hydraulic and the electromechanical actuators which can be used in aerospace, defense, marine and industrial applications. Then you have series actuators which are produced which produce electric and electromechanical actuators used in industries like robotics, medical devices, automation systems. And seventh is the Zaber. It will produces the electric linear actuators, motion control systems used in research industries, medical devices, semiconductor industries. And you have EC card, where it produces hydraulic, pneumatic and rotatory actuators. And here these will be used in industries like industrial automation, construction and the heavy machinery. Okay, so this was about the industrial sensing and actuations. Thank you.